All right, now on the second part, part two. We've talked about what the first derivative does for the shape of our graph, but what about the second derivative? So that's what part two is going to be all about. Now here I've got two different graphs, very similar. Both f and g are increasing functions on that open interval a to b. They are both always going up. Both points connect, both from point A to point B, but they're different. It's about the curvature. F has this kind of curvature where it's kind of pulled down, but everything is it's curving towards the up. G is kind of curving towards the downside. That's going to be the difference here. Now, thinking about this, if we go back to our derivative, all of those tangent lines, our tangent line is getting steeper and steeper in graph F. If we look at our tangent line, the slope of our tangent line is getting less and less steep, more shallower. That's the rate of change of the rate of change. That's the second derivative. And so we're going to be looking at the second derivative, how that affects that shape of the graph. Now to define this, we call this concavity. So in these two graphs up above, we have two different examples of concavity. The first graph, all of the tangent lines on that interval, our graph is currently above any tangent line. So we take our tangent line, the graph is always above them. So like at any point, take the tangent, the rest of the graph is above the tangent line. When we have that case, we say that is concave upward on that interval. So graph F is concave up on the interval AB. If we look at the second graph, any tangent line, our graph lies below the tangent line. It's curved down. We say that is going to be concave downward on that interval. Now the way I see this is kind of being cupped up, bowled up, whereas G is cupped down. And you might remember words from physics or past experiences like concave or convex. We're just going to be concave. Concave up, our graph is curved up. Concave down, our graph is curved down. Thinking about the progression of the tangent lines, that's where our second derivative comes in. We'll first look at another example. We have a whole lot of curvature going on here. Now, from A to B, our graph is curved down at each of those points. From A to B, we're going to be concave down, CD for short. At B, we switch. Our graph is going to be curved up. And I think about like if you're pouring water onto this graph, water or liquid is going to pool in that section. If we pour water, or if it's raining onto the section between A and B, it's not going to pool on top. All the water's going to run away. So water's going to run away, concave down. If our water's going to collect in that area, it's going to be concave up. At point C, we switch again. It's going to be concave down in that section. At point D, we switch. D to E there, we are concave up again. E to P, we're still concave up, but we pass through that cusp point. And at point P, we switch once again. We are back in concave down from P to Q. So we're concave down, concave up, concave down, concave up, concave up, concave down on those sections. Let's see what happens. What we're looking at here is our concavity test, looking for the concavity of a graph. If the second derivative, so it's all about the second derivative here. If our second derivative is greater than 0 for all values in that interval, our graph is going to be concave upward. If our function is, the second derivative is less than 0 for all values, then it is concave downward on that. And thinking second derivative, we take our tangent lines and we look at the progression of slopes of our tangent lines. Well, that's going from steep to less steep to actually negative there. But our slope is decreasing over that section. So the second derivative, the slope of the slope, is negative. If we look from B to C, the tangent lines would be increasing in slope from a negative slope to a 0 slope to a positive slope. So the slope of the slope, the rate of change, is positive. F prime prime is going to be greater than 0. So in short, anywhere where our derivative, anywhere our second derivative is positive, we're concave up. Anywhere where our second derivative is negative, we're concave down. Now these points where we change concavity from going down to up or up to down, we call those inflection points. So a point on a curve is called an inflection point if we are first continuous at that point, and the curve changes from concave up to concave down or from concave down to concave up. So point B is an inflection point. Point C is an inflection point because we change from up to down. Point D is an inflection point. Not an inflection point, change in the graph, a cusp. Point P is again an inflection point because we change from concave up to concave down once again. Inflection points might exist when the second derivative is 0, similar to like the critical points might imply the existence of a maximum or a minimum, or it just might be a horizontal tangent. Let's see this in action. So let's go on and analyze this curve. Y equals x to the fourth minus 4x cubed. What I would like to do is to identify, and I put this out of order, we're going to identify intervals of increase or decrease. We're going to use that to identify maximum and minimum. We're going to take the second derivative to identify any potential points of inflection, and then identify intervals or concavity. And we're going to sketch the curve. So y equals x to the fourth minus 4x cubed. I'm going to take our first derivative. So I'm going to say y prime. Simple power rule, we've got 4x cubed minus 12x squared. I'm going to rewrite this. I notice that 4x squared is a common factor. I'm going to take out 4x squared, and it's going to leave me with x subtract 3. Critical points are going to be x equals 0 and x equals 3. I'm going to use this and my sign chart, my number line. I'm going to partition my number line using those critical points, 0, 3. And I'm going to identify where is this graph increasing, decreasing, and therefore getting maximums, minimums. Now, I'm going to pick some number to the left of 0, -1. Consider it in my factors. So -1 squared times 4 is positive. -1 minus 3 is going to be negative. So any number to the left of 0 is going to be 1 negative, it's going to be negative. I'm going to pick some number in between 0 and 3, say 1. If I plug in 1, we've got 4 times 1 squared multiplied by 1 subtract 3. That's going to be positive and negative again. Okay. So 0 is a critical point, but it's not a maximum or minimum. It's not going to be an extrema. Next up, I'm going to pick something beyond 3. So 4. And if we test something there, we're going to see that that's going to be positive. So we are decreasing whenever the first derivative is negative. So we are decreasing negative infinity to 0, 0 to 3. Notice I'm not including 0 because that's a 0. The gravis, the tangent line is 0 at that point. That's a horizontal tangent. Pauses, things like x cubed. Our function is increasing from 3 to infinity. Right now our graph is going down, and then going up. It kind of falls in line with x cubed, x to the fourth would look something like that. We're going to have a, ooh, that's going to be a thing right there. So we're going to have at least a local minimum. Next, I'm going to take my second derivative. I'm going to go back to that first derivative before it was factored, so that we don't have to use the product rule. Second derivative, that's y and not y prime f prime. That's y prime. Y prime prime. The second derivative is going to be 12x squared minus 24x. And I recognize I can factor that. It's going to be 12x, x subtract 2. The second derivative set equal to 0 will give us possible points of inflection. It's going to be at x equals 0, x equals 2. I'm going to do the same thing, but this time I'm going to partition the number line using the possible points of inflection. 0, 2. This is y prime. I'm going to do this sign test once again. I'm going to pick some number less than 0, pick some number in between 0 and 2, pick some number greater than 2. Test, is this positive or negative? So picking something to the left of 0, say -1, that'll be -12 and -3. Okay, negative, that's going to be positive. Oh, concave up. I'm going to pick something in between 0 and 2, say 1. It'll be 12 multiplied by 1 minus 2, 12 negative, that's going to be negative. Concave down. I'm going to pick something beyond 2, say 3, that's going to be positive, that's going to be positive. Concave up. All right, so we have a minimum, I'd like to mention that. Minimum is going to be at 3. And then plugging in 3 into our function, that's 81 subtract 4 times 27. 4 times 27 is 108. 81 subtract 108 is negative 27. Negative 27. We are concave up. Negative infinity to 0. And again, from 2 to positive infinity, we are concave down from 0 to 2. And we have points of inflection. X equals 0, x equals 2. So let's go on and sketch a graph now. Now we have y equals x to the 4th minus 4x cubed. What we know from algebra is if we factor out x cubed, we're going to have x subtract 4. We have set points that we know. There's an intersect, 0, 0, 1, 2, 3, 4. We have a y-index intercept at 4, 0. Now we know that we have an absolute minimum, and I know it's going to be an absolute minimum because we have a quartic polynomial, so it's increasing to the left or it's decreasing, concave up, and then we're concave down, and then we're concave up. We're going to be points of inflection are at 0. We know that point. And x equals 2. If we plug in x equals 2, we're going to have 16 subtract 4 times 8. 4 times 8 is 32. 16 minus 32. We're going to have a point of inflection at 2, negative 16. Put that down here. We're going to have our minimum value at 3, negative 27. So 3, negative 27 is going to be down here. We are concave up, concave down, concave up. Let's keep on stretching. There's a sketch of our graph. Happy days.